Hi. So I've got something else that I just discovered, and it's kind of fun. Of course, it's fun. When do I ever discover stuff that's not fun? So I've been playing down here in the lab with my 9,000 volts AC transformer, just zapping stuff again. And the reason I'm doing it is because I'm sorry, this is a really weird angle. You'll see why in just a minute. Facebook sent me a notification a couple days ago about an experiment I had done either a year ago or 2 years ago, and it showed me the video of it, and I was like, oh, I forgot how cool that was. And it was just suspending an electrified screwdriver over a plate of baking soda and creating the butterfly patterns that we've talked about many times before. So I just wanted to start playing with that again. And then I got the idea to start changing the electrodes, and I've been collecting a bunch of different type of electrodes ever since I started doing these type of experiments, because apparently the shape of the electrode makes a difference. And I've been studying Helmholtz coils. If you don't know what those are, just look them up. They're kind of fun. They're just two coils next to each other. Electricity goes through them, and they create a very interesting magnetic field in the middle of them. And the research that I've been doing shows me that if they occur in the earth, there could be some interesting geological formations associated with that. But that's another topic. Let me show you what I've been doing today, and here's why I'm in such a weird position now. I'm going to flip the camera around so you can see this. Now, let me do this. This should work. I'm going to take the camera out of its holder and just give you the gestalt of what we're dealing with here. So there's my popcorn tin from a year or so ago. My little holder for the phone. And yes, that is a tuning fork. I got it from Eileen McCusick. I've been following her research as well. That's the 176 hertz tuning fork. But yes, I'm using it as an electrode. And you see this white wire hanging down right here. This is just an alligator clip. It's clipped on there. And of course, it's connected to that little bolt. And as you remember, that little bolt goes all the way through the table and is connected to that wire, which runs down there and is connected to the transformer. That's the 9,000 AC transformer. Okay? So the other wire, this little red guy, and yes, I've been working on Christmas lights, is connected to the other bolt right over there by the rinse water container. That bolt is also goes through the table and is connected to the other side of the transformer. Hello, Christmas lights. Anyway, back to the experiment. The top of this is, of course, filled with baking soda. Right there. I just spread it on, didn't really do anything amazing with it. But I started playing with it. I started electrifying the tuning fork, and I saw something that I have never seen before. We've all seen magnetic fields when you get iron filings around a magnet. In fact, my box right up there, full of iron filings, I've done that many times before. But this is the first time that I've ever seen an electrical field. You're about to see it. It's pretty cool. So let's put the camera back in its cradle. Excuse me for just a moment while I get this set up. Because this is critical to get the angle just right. That's not gonna, well, hopefully I won't run out of battery. All right. Check this out. 3, 2, 1. Everything hooked up? Everything's hooked up. I did adjust it just a little bit because it was arcing and I didn't want it to arc. All right. So that's starting to get, whoa, pause. That you started to see it right there, but it's going to be a lot more visible here in just a second. I have to get, okay, there we go. Can you see that? Yep, we can. Watch. You can already see what you're looking at is in between the tines. Look at that. Whee! Creates a little fountain. What I'm scooping it with is something from my day job. This is actually a sample of a blind slat, but it's for a company it's not even in existence anymore. So instead of throwing it away, I bring it down to my lab and reuse it. But look at that. Just fountains it up. But what we're looking at here is the actual electric field, which is just something we just don't see at all in everyday life, and yet there it is right there. Now, one thing that that the camera is not picking up, but if you pay attention, you could see. You see how here's the end of the fork, and here's the other end, and this is probably about 8 inches from the base of it, from the yoke of it right here to the tip. And as you notice, it's white along probably about a third, just over a third of the distance right there. And anytime I bring the powder up into that area, it acts like there are 2 rolling pins. Imagine that one of the tines, the one on the right, is spinning. Well, and see, this is what I can't quite tell. This is hi. Thank you. This is what I was hoping I could get some feedback on, whether anyone can tell which way the powder is moving. I mean, there's clearly an up motion, there's clearly a down motion, there's clearly a vibration, just a bouncing motion. But I've been studying this for about 15 minutes, and I'm still trying to figure out which way it's moving. Now, the other thing you'll notice is that if I pile it up underneath the tines or the electrodes, the actual mound will erode. So we know there's motion, but what I can't tell is if the electric field is, let's see if I can draw this in the air. It looks to me like the right side is rotating counterclockwise and the left tine is rotating clockwise, which is producing a net downward thrust. Maybe. But I can't quite see it, because if it's putting a downward thrust, then you would think that the mound underneath it would be built up, not eroded. Now, there is also a tiny amount of powder that is just blowing away, like in any sandstorm. It's coming up through here and blowing out into the lab, getting all over the lab bench. But if you can tell which way that's spinning, that is really hard to see. But it clearly is spinning. And it looks like it's 2 tubes that are spinning. The other thing that's kind of interesting is I can bring the powder up all along the channel, but it really only is activated right here at the ends. Which is interesting because the entire length is active. But see, if I bring it up here or back down here, it's not doing anything. And as I bring it closer, we get more action, more. But see, it's only in that last third that we really get motion, and it's right at the end where it really gets vigorous in the action. I'm open for comments or ideas as to why that's the case. The field is clearly along all of it, but it's strongest right here at the end. And if there is a net downward force in the middle, if those cylinders of electric potential are, or not potential, but if the kinetic force fields are spinning down the way I think they are, where is it drawing the material up from? That's what I can't see. It looks as if there is some magnetic attraction too. If you see those little fingers that mate and then break between the ends of the electrodes and my little scoop shovel thing here. It doesn't always happen, but just here and there. And see, there's clearly erosion. In fact, if I bring it closer to either electrode, the erosion becomes more pronounced. And see, there's the little tendrils there on that left side again. Hope you can see those. It looks like magnetic attraction, which is interesting that it doesn't always happen. There it is on the right side. Look at that. They're almost like wet spider webs. And then the other thing, hopefully this is visible, but there is actual buildup on the electrodes themselves. Watch, I'll wipe it off. Right there. And right there. So it's building, and of course it's building up on top, but not as pronounced. Is there any on the bottom? Not really. But right in between, you saw that huge mound-like buildup. I'll do it again. You can see it slowly building up right there in between the two tines facing each other. A little bit on the top. Ooh. All right, my arm got sore. Oh, let's try this. Bob, I'm going to see if I can bring you on. Let's see if I can do that. If you don't want to come on, that's fine. Oh. All right. I will try that later then. Let's see if I can zoom in on that. There we go. Ah, there we go. Let's try it this way. Watch. Tell me that's not cool. Tell me that we're not envisioning essentially the shape of that electric field. Now, granted, I'm sorry if I meant to say that we're seeing an electric field. We're not. We're seeing the electric field's influence on baking soda, is what we're seeing. Can't really see the electric field, but just the fact that we see it at all, that we can see it or see it in any form, I think is pretty cool. And that's just with baking soda. Interesting. When I make contact with it, it's like I'm short-circuiting it. Now, as far as movement again, I don't know if you can see this. Oh, you sent a photo. Let me take a look at it. The baking soda is actually bouncing up and curling away in this. Let's see. Oh, you can't quite see that on the camera. Let me back this off just a second. The baking soda right here is arcing up, and it looks like it's bouncing over. There's definitely a curve pattern here. Let's see what Robert's saying. Oh, sorry, Robert, your comment just came and went. Oh, let's see, you were talking about a magnetic field. Oh, wait, whoa, where did it go? Sorry, Robert, my phone will not let me read the comments at the same time. I pulled it up and it just went goofy. I will answer those after I get done with this. But yes, it clearly looks like a magnetic field. And if I knew how magnetic baking soda was, that would probably tell us how much of this reaction that we're seeing is magnetic and how much of it is electric. Is the electric field. that we're visualizing. And we know that modern cosmology is really interested in magnetic fields in space, but will they admit to electric fields in space? Not yet. Anyway, okay, so now that I've been playing with it for a few minutes, you can see the buildup, again, along the inside tines. There's a little bit here. Oh, that's interesting. Just bringing this is a bamboo skewer. I'm just holding it in my hand. Do you see that just jump? Look at that. Just jumping off as if it's reacting. Like it's reacting to it. And then if you look on this side, see if I can bring this over. Look at these cute little, almost look like icicles right there. Let me see if I can zoom in on that. Try putting the green magnetic, let me see if I can get back to that comment. Will do. Robert says, try putting that green magnetic field detection film to see if it coincides with the material. I will try and do that. See, and there's that buildup again. Couple things I want to show. Okay, I'm going to turn this off because I have to reach over it, and I really don't want to zap myself again. I've done that many times. There's my magnetic green detection. Oh, that one's has had a bad day. I don't know what's on that. Okay, I'm going to lean that right up against it and see if we get anything. Okay, it's energized now, and I see nothing on that card. Let me do this. See if I can make that a little bit more visible to the camera. Okay, I'm shining a flashlight on it. And 3, 2, 1. I see nothing. Now, granted, that magnetic field is oscillating 60 times a second, which is probably way too fast for this green little card to even register. It does very good with nice static magnetic fields. I would be very surprised if this could pick it up. However, if I could zoom in on it, we could probably see tiny little particles dancing around. But I see nothing. I see no motion on there at all. And I'm about 12 inches away. My eye position of the card. The camera won't be able to see this as well. Let me see. Energizing. Oops. I'm going to get my magnifying glass up here. See if I can see anything. I don't see any movement at all on that card. I mean, we know there has to be a magnetic field, you know, with that electric field being in flux, in motion. There has to be a magnetic component to it, but it is not registering on that card at all. Robert, thanks for that idea. That was a good idea. All right, let me go back and show one more thing. See if I can remember what it was. But if you notice that the pile just gets worn down very, very quickly. Watch. The pile went from, it's already down probably almost a half an inch from what it was just a second ago. Now to make it a little bit more dramatic, I'm going to shut it off. I'm going to pile it up again. All right. Take a good look at it. Let me get spot on it. Okay. Got a good look? Here we go. 3, 2, 1. That's a good shot. Wow. Wow. Look at the top right there. Look at that. Hello, Monument Valley. Tell me that little pinnacle right there doesn't totally look like what we see in Monument Valley. Now, there is one difference to it, one very big obvious difference, and that is there is a very sharp point at the top, whereas the Monument Valley monuments are pretty flat on top. Of course, again, this is AC 60 cycles. I doubt that whatever formed Monument Valley was at 60 cycles AC, that we get the same type of features with electricity. I don't know if the camera's picking this up, but there's a bunch of very, very tiny, small pinnacles there as well, aside from just that big one. From this angle, I don't know if the camera's picking it up, but there is a lot of just bouncing motion, and it's hard to tell if it's a cylindrical motion or not. In fact, it looks like a fountain. There are particles coming up above the tines as well as below the tines. Oh, wow. Oh, geez. Bye-bye to that. That's interesting. It's almost like it was pulsing. I wonder why it did that. I hope the camera picked that up. What I saw is that all of a sudden it became very reactive and just mowed down a whole bunch of it, and then it just kind of relaxed. It's just kind of settled into a steady state of mild erosion. I'm going to scoop up the surface again, turning it off. Scooping it around. Actually, that's the wrong tool. Let's use this one. I'm going to do this one more time. See if I can get most of the baking soda underneath the tines, because it is pretty spread out along the top of this container now. Okay. Let me do one more thing. So you get a view. Okay, so that's what we're looking at. Camera's going back in the cradle. Zooming back in. And here we go. 3, 2, oh, nope. Nope, sorry, false start. Come on, light. 3, 2, 1. That's just cool. That is just cool. I tried this with my screwdriver and the other probes that I had. I just didn't get this effect, which is kind of fun. Now, of course, someone's probably going to say, well, what happens when you strike it and make a tone? Good question that didn't get asked. That's what happens. Nothing too big. I don't really notice anything big happening. Geez, it's like a rooster tail. It's like water coming out of the back of a motorboat, speedboat. But once again, it's not along the full length. It's just basically down here in the last third to a quarter of the tines. You get a little magnetic, what looks like a magnetic reaction. All right. So that was fun. So, any questions or comments? I'm a good for listening to those because to me that looks like we're envisioning the electric field, which is something that in all my playing around in the lab and whatnot, I have never seen before, which is actually pretty cool. And it's baking soda. I mean, it's clearly getting pulverized and going throughout everywhere. But what I love using about it is even if I breathe it in, it's like, oh well, I've alkalized myself. Oh no, that is a good thing. Anyway, if anyone has any ideas, comments about it, please post them. I would love to explore any ideas with it or get further explanations on what we see here. If you have any other ideas on how to reconfigure that, what to add to it. Oh, let me add this. I have taken my magnets. You know, I've got my ceiling magnets. Y'all seen that? That's all my magnets up there. Quite a few. That's the neodymium side. That's the the ceramic magnet side. But I've taken the magnets and I've attached them onto the tuning fork. Oh, it's freaking strong. They just pinched my finger. I've taken two of them. Ow! That hurts. Taken two of them, put them side by side across the tine. And now they're gone. Like that to see if that magnetic field would interfere with that fountain. Didn't seem to. Not at all. That's fine. It either does or it's not. That's the way I had them on the tine. Didn't do anything. So, not surprising. But the reason I do that is because if telluric currents, and telluric currents are, of course, currents of electricity that flow underground. If telluric currents are interacting with atmospheric currents, aka Birkeland currents, you would expect, oh no, I'm sorry, I said that wrong. If telluric currents are going through the ground, which we know they are, they should be interacting with all the minerals in the ground, many of which are magnetic. Anytime they hit nickel, iron, or cobalt, there's going to be a very strong magnetic component because those are the three things that are magnetic. Not to mention all of the weird paramagnetic and diamagnetic minerals and compounds that are out there. Which just, when I start thinking about that, it just almost blows my mind thinking about all the different configurations that the electric field could take when it hits these different substances below the earth. You know that they're there, and you know that they're doing something, but what are they doing? Now, as much as I would like to see that, we know from David Talbot et al. That when the earth went through those experiences with these huge manifestations of electric and magnetic fields, it was not a good day for the earth at all. And that's one of the reasons why everyone went underground hiding. So part of me wants to see that, and part of me doesn't want to see that at all. Part of me is very happy to live in the nice, calmed down state that we live in now. But to think that that was, just 12,000 years ago is amazing. Amazing. Okay. Well, now what else are we going to do? I'll go find something else. Anyway, have a good day, everybody. Science! Still science. 2, 1.